discuss today one of the most important applications of hydrostatics, that is calculation of pressure on surface, calculation of force due to pressure on surfaces. So we will start with plane surfaces and then we will move on to curved surfaces. So let's start with plane surfaces. So suppose you have an area here. So area here is A, and say this is in the XY plane, right? Please follow the 3D diagram. This is X axis, Y axis, X, Y and Z as they say. So X, Y and Z like this. So this area A is in the XY plane as you can see, and the pressure is acting like this, P. So what is the force due to pressure on this plane surface area? Simply you know that the force is going to be P multiplied by A. So here it is, the force due to pressure on this surface F is equal to P multiplied by A. Now let us calculate pressure, force due to pressure on a curved surface, and rather force due to uniform pressure on curved surfaces. So this was actually a plane surface, right? Now let us consider curved surface. Say for simplicity, let's consider a curved surface like this. Okay, this is just a view of the curved surface. This is what the curved surface looks from the front. Say this is a quarter part of a cylindrical shell like that. So the actual cylindrical shell, the quarter part of the cylindrical shell. So this is the shell. I hope it is clear, right? So there is the center of curvature. This line is the axis of the cylinder. So this line here, this line is this dot. So this is the axis of the cylinder, and say uniform pressure is acting on this curved surface. So let's draw the pressure, and so as we know that pressure acts normal to the surface in contact. So here this part is filled with liquid, and say uniform pressure, liquid or gas, whatever it may be. Maybe it is filled with the fluid in general, because in liquids you know pressure varies with height. So we'll take a gas for the time being. So pressure is constant at all points on the curved surface. So let us calculate the force on this curved surface. So let us take a small differential area of this curved surface. So this area, differential area, is dA, right? And we'll break up the force into two axes. Let this be X axis, and this, say the Y axis I'll make downward, because as we know force on this surface will be acting this way. So one component will go there and the other component will go downward. So we have considered the X and Y axis like this. So this is the area dA. And what about the pressure or force due to pressure? So force due to pressure is this. So this is P multiplied by dA. Now what about the components of force? Now we will calculate the components of force. The X component here and the Y component downwards. So that's the X component. So this will be, if this angle is theta, so this is P multiplied by dA cos theta. and this component will be P multiplied by dA sin theta. Now, if this angle is theta, so if you take this area A, suppose, see, as this is a very small area, so this length is dl, this length is dl, and there is a width, and suppose the width, as you know, the width we will consider as b. So what is this dA equal to? This dA is equal to this width multiplied by the small length dl. So that's dl, and the width goes this way, right into the plane of the board. So this dA, this area of this strip is equal to b multiplied by dl. And so about these angles, say this length, if you split into components, then if this angle is theta, right, or make it bigger, this angle is theta. It's the vertical line, this is the line dl, and this angle is theta. Now, so what is this component of the length, or this part of the length is dl cosine theta, and this part of the length is dl times sin theta. So as you see, dl cos theta, so the projection of this area perpendicular to the x-axis is dl cos theta multiplied by b. So I'll show it in a different diagram. What is it all about the projected area? See, so we are dealing with this small area dA. So as you see, this dA is equal to this b multiplied by dl. Now, this dA is actually a rectangular strip, because see, this is actually a curved surface, but we have split it into small rectangular strips, like thin slips of paper. Now I will draw this dA for you. This is the front view of dA, but in a three-dimensional diagram. So this is the area dA in a three-dimensional diagram. I don't think it is still clear to you. Let me complete the diagram. I think it will be clear there. Now, so x and y axis. Now, what I meant by projection is this. So as you see, this is the x-axis. This is the x-axis. That downward goes the y-axis. We'll deal with y-axis a bit later. Let's look at the x-axis only. So this curved area is dA, and this happens to be dA cos theta. See, dl cos theta, right? So this length is dl. This slant length is dl. So this length is dl times cos theta. So if this area is dA, now this area happens to be dA times cos theta, because dA is dl multiplied by b, and this is the same with b multiplied by dl cos theta makes it dA cos theta. And the force, the x component of the force on this small rectangular strip. So this is the x component of the force. So as it is force on this small rectangular strip, so I will make it dFx is equal to pressure multiplied by dA times cosine theta. Now this dA cosine theta is dA cos theta is the projected area perpendicular to the x-axis. So next, so I hope this is clear, right? Simple as that. See, this area is dA. So the x component of the force. So the force on this area dA acts along this direction. So make it dF. So this component is d of fx, and this downward component will be d of fy. So d of fx is equal to p multiplied by dA cos theta. See that. So I hope it is clear in this diagram. This dA cos theta is projection of this area perpendicular to the x-axis. By projection we mean that suppose there is a parallel beam of light incident and the light rays are perpendicular to the x-axis. Light rays are parallel to the x-axis rather, and there is a screen. The screen is perpendicular to the x-axis. Then the shadow of this area dA cast on the screen is dA cos theta. Same way, we will learn about dA sin theta, which is projected area perpendicular to y-axis. And in the same way, projected area means there is a beam of light parallel to the y-axis, and that will cast a shadow on a plane which is perpendicular to the y-axis, right? So the light rays will hit the surface normally and cast a shadow of the area, this strip of area dA. So let's draw the light beam from top. There it is, there is this one, there it is, and there it is. And let's draw the shadow. Shadow means projection. So this area is dA times sine of theta, and the force, the y component of the force which acts downwards is, we write it like d of fy is equal to the pressure acting on the surface multiplied by the projected area perpendicular to y-axis. So P multiplied by dA sine of theta. Right. So we have calculated the force due to pressure on the small strip dA. Now we will calculate force due to pressure on the curved surface. We started with the quarter shell, right? So we will continue with that, and remember also it is force due to uniform pressure. That is, the pressure is same at all points on the curved surface, right? Mainly pressure due to gas happens to be like that, not due to liquid. Due to liquid, pressure varies with height. So we are not talking about that case right now. So let's take this curved surface. So this was the quarter shell. Quarter shell, this has got a width. Where is the width? Width is there, perpendicular to the plane of the board. Now, as the pressure acts normal to the surface, and as per our choice, the x and y axis were this: x towards the left and y towards downward direction. So now, as we see, due to this small strip dA, we have taken this projection of this area perpendicular to the x axis and perpendicular to the y axis. So we are going to do that. We are going to add up all these projections, right? So due to this curved surface, say you take a small part dA, you have this projection, right? So all these projections will add up to give you the projection of this area perpendicular to the x axis. So what you will get is and here also, so projection of this area is a plane surface. Here also and here also, it's a plane surface. So the force, remember, uniform pressure, so that is P multiplied by projection of the area, say dA, sorry, not dA, so it's AX. AX, later on we will let you know what AX is. And on this surface, pressure is P multiplied by AY. So AY and AX, so AX is projected area perpendicular to x axis, and AY is projected area perpendicular to y axis. Now, what are these AX and AY? If you look at the quarter cylinder, then it will be clear. So actually, this AX and AY. So AX is equal to B times R, and AY is also B times R in this case. Why? I will show you by a three-dimensional diagram of the cylinder. So this was it. This is the quarter shell. Now, as this is a 3D diagram, we will have the width also. So there we can draw the width. So we can draw the axis of the cylinder is that we draw this line, this line, this line. So this line is the axis of the cylinder, and let us draw the projections of these areas. Is it straight? Yeah, reasonably good. So this one, now we are drawing the projected area perpendicular to x axis. Then we will draw for the y axis. It will be same and symmetrical. So that's it, and one from here, that's it. Fine. So there it is. So this is the projected area AX. So as you know, as this part is this part was the width B. So here also this part is the width B. And this part, see, this is the axis of the cylinder, so this is the radius. So this part is the radius R. So there you see the projected area perpendicular to x axis. AX is B multiplied by R, as I have written here. AX is equal to B multiplied by R. And the thing will be symmetrical in the y axis also. So just let me draw. It's quite obvious that the projected area perpendicular to the y axis will also be the same. Should be a bit from here. Yeah, so this is our AY, and this is also equal to B multiplied by R. It's same and symmetrical. This is the case for the quarter cylinder. Now we will move on to calculate force due to uniform pressure on half cylinder. If you take a half cylinder, then what will be the projected area? So that's okay for the quarter cylinder. Now I will erase this one. So force due to uniform pressure on half cylindrical shell. Now I thought I will draw a 3D diagram. Begin with a 3D diagram. This is it. This is a half cylinder, as you can see. Half cylindrical shell. From the front view, if you view it from here, it's simple. It's a half circle. And the width goes directly, width goes into the depth, right? Into the plane of the hole goes the width B. Suppose the width is B, it's here, and in this 3D diagram, obviously the width is, it can be shown quite well in the 3D diagram, this one, B. And the radius is R. Now, what about the forces along the x and the y axis? Say this is the x axis, and as you can see from symmetry, so as it is uniform pressure like this, so as this is the x axis and this is the y axis downward, the total force along the y axis will be 0, because say let us choose one element here, the force is applied this way, and the other element symmetrically here, this is the force. So the vector sum of these two forces will be towards x axis. So every element you choose downwards will have a pair upward. So the y components of the force will cancel, and hence the y force is 0. So we have to deal with the x force only, and the projected area perpendicular to the x-axis is needed, and that is what you can see from here. Projected area will be this. Again, remember that a light beam, this is a light beam traveling parallel to the x-axis, casting a shadow on a plane perpendicular to the x-axis. So this is the shadow which is cast, which is a rectangle of this side as B and this side as 2R. So the area, projected area, so let's write it AX. So here the force, obviously the force is along the x-axis. We can write Fx only because Fy is 0. So Fx is equal to P multiplied by Ax. And what is Ax? You can see from here. Ax is equal to B multiplied by 2R. So 2RB. That is Ax. Right. So now we will calculate the force due to uniform pressure on a half or on a hemispherical shell wrap. So I will erase this diagram. Force due to uniform pressure on a hemispherical shell. That's quite simple. From a certain view, this is a hemispherical shell, and as you know, pressure will act normal to the surface as in all cases. So the net force from symmetry, you know, the net force will be along this direction, and the force will be equal to P multiplied by A. Which area it is? A, again I tell you, this area A is the projected area perpendicular to the direction of the force. Obviously the force, if you this as the x-axis, the force is along x-axis, and you have to consider the projection of this area perpendicular to the x-axis. So if you have light beam from here, this is the surface. Actually the projection of a hemisphere is a semicircle. You see this one. This is the sphere, and projection of this area is a semicircle of radius r. The radius is same as that of the hemisphere, right? So here, as you see, A projected area is equal to pi r square, and the force is along this direction. Force is in the direction of the x-axis as shown in the diagram. So force is equal to pressure, uniform pressure multiplied by pi r square.